still feel a little bad about having neglected the theory of relativity because there are a couple of points. Well, there's a major point that I never really got into until the last lecture, where I was trying to show you how you set up synchronous clocks. It's a very important idea of how you set up synchronous clocks in systems that are moving relative to each other. The idea being that in one system you can set up clocks synchronously by this scheme of having a set of observers. I wish I had real time to go into it, where you set up clocks preset to certain distances, and then by sending light signals, you can get the clocks to their hands to be moving together. And in one frame of reference, and what I was trying to get at is the idea of relativity is if you have one thing moving with respect to another, when you make measurements in the different systems, lengths and times will measure differently in those two systems, just because the systems are moving with respect to each other. And usually the reason that happens is because their clocks run differently. I don't really have time to go into it. Maybe some time, if we really have a break, I'll go into it in greater depth. But that's the origin of the issue. And all it has to do with is relative motion of one system with respect to another, like a train with respect to its tracks. The people on the train will see one set of clocks running a certain way, their clocks. They can synchronize their clocks to run with their hands all pointing in the same direction everywhere in the train. And the people on the tracks will have clocks that run with all their hands pointing in the same direction in their time. But when one system observes the other, the clocks will not be synchronous. Some will be running faster than others. And that's what gives rise to the length difference measurements and the time difference measurements. But what I wanted to make sure that I mentioned to you, just basically in passing, because we can't go in great depth, is this idea that, interestingly, we said in the beginning, I mean, you brought up this point, we said magnetism and electricity were two different things. Electricity is charged, and magnets are a rock that points in a certain direction. What do they have to do with each other? You want to start out thinking they're different. Then we progress a little bit, and we realize that from electricity, you could get magnetism. This was what Maxwell said. If I have a changing electric field, it acts as a current, and it can produce magnetism. So first, we tell you things, and then we sort of get deeper and realize that we tell you something quite different. So once magnetism and electricity were two different worlds. Indeed, an electric charge does not attract a magnet, and a magnet does not attract an electric charge as such. But then we realize that when you have moving things, currents, or moving magnets, you can get that magnetism will make electricity. That's the Faraday effect. That magnetism, changing magnetic field, will produce electricity. And from the Maxwell displacement current, we found that you could get a magnetic field from a changing epsilon d phi electric dt. So they're not so far apart as we originally thought. Now, with the relativity theory, we can actually show where magnetism is, in fact, arises from electricity. And we do that by saying, if you have a moving charge, which is, well, we start out this way. If you just have a simple charge, we say that that is not affected by electric current, because that's just a static magnetic field, and this charge, say, is not moving, v equals 0. On the other hand, if the charge starts moving with a certain velocity, now what does it mean to have a current? Well, our conventional current is plus charges moving in this direction. And maybe the minus, well, this is actually backwards from what really happens in, say, metals, where actually it's the electrons that move. But we just have this convention about positive charges moving. So let's say the negative charges are left behind, and they're basically stationary in the wire. Now, if the charge starts moving, then it's moving in the direction of, let's say to the right, the same direction as the current is moving. And we have the negative charge is still stationary. Now, let's look at it relativistically. Suppose we change our frame of reference. Suppose I take the point of view that, with respect to the charge, this velocity is less. Or what I could do is take the frame of reference where the charge is stationary now, even though it's moving. So what I have is the positive charge is moving this way, and I have the negative charge is moving this way. But the difference is that because they are moving, it's moving with respect to this somewhat slower, the negative, let's see now, the negative charges will be moving backwards, and what you get is that the length here looks contracted, and so you have, let me get this clear. Okay, well, we could even take this point of view here. This one is moving. Now, if it's moving in the same direction as this, then its velocity is, relative velocity here is lower, and the velocity of the negative charges is greater, so that the negative charges, having the same original density, now the length in which they are contained is reduced by the length contraction, as seen from here, so that the negative charge has a larger charge per unit length. This lambda is the charge per unit length, so that it creates, if this were a positive charge, if this is positive, the negative charge is moving leftward, but it's contracted more, so there's a force now acting. Because the negative charge has a larger charge density, there's a force now acting, pulling the charge toward the wire. And that's what we said happens when you have a current moving with a charge moving with respect to a moving current like this, that there is a force acting on the current. So we have derived this force actually from a relativistic contraction of the charge density within the wire. So what we've gotten here is that you can describe what happens when a charge starts moving with respect to a current, that this will give you an electrostatic attraction between the moving charge, Q and V, when it's moving with respect to the wire. And so we've derived, and that's exactly what the magnetic field does. So it's a way of saying that, in fact, the magnetic field arises from a relativistic effect. So we come around in a way full circle and said that, in fact, electricity creates magnetism by relativistic effects. I just wanted to pass that on to you. It's in the notes here, and it tells you an interesting result of the relativistic approach to things. The other thing I did want to mention to you, of course, is that we have the idea that the mass of something, or its momentum, depends on its speed, which says that it's harder and harder to accelerate things because F equals ma. This m will be a function of velocity, and so it gets harder and harder to accelerate things, acceleration being force over mass. As the velocity goes up, the mass, it's a little bit controversial point actually, but we can take it that the mass will vary this way. In fact, as v approaches c, the mass gets very large, and because it gets large, you can't accelerate the thing for a given force. It accelerates less and less, and therefore, in fact, you can't get up to the speed of light because the thing you're trying to accelerate gets more and more hard to accelerate as you get closer, until the mass gets virtually infinite, and then you need like an infinite force to make it accelerate any further to get its speed. The other thing that Einstein's relativity was famous for is that mass intrinsically contains energy to the amount of a rest mass, this object here, m0, this is the mass that a thing would have if it were not moving. And intrinsically, a thing has an energy equal to m0 c squared. And this is what gives rise to nuclear energy. And we'll see this again, I think, later in the course when we talk about binding of particles in nuclei. We'll find that a nucleus has a certain number of particles in it, but its energy is a little bit less than the sum of the particles because there's binding energy that holds them together. But nevertheless, if you can convert some mass to energy, you get a lot of energy because you're multiplying by a very big number, c squared. And so each material particle, if it has a mass, it has an energy content to it when it's even at rest. And conversely, if you have enough energy, you can create matter. And that is done too, where you can shine in very intense, very high frequency energy, electromagnetic radiation, and you can create particles. But if you do create particles, you must conserve charge. That is to say, you'll create a positive and a negative together, because charge is conserved. We never create charge. We only, at best, separate it, plus or minus. And when minus and pluses get together, like you can get a positive electron and a negative electron, they can join together. You lose the mass, and that will come radiant electromagnetic energy, a lot of it, per particle. I mean, this doesn't look like much, 10 to the minus 4 joules, but on the scale of subatomic particles, it's a lot. And of course, there was the joke about how did Einstein come up with E equals mc squared? Well, he tried ma squared, that was no good. He tried mb squared, that was no good. So he tried mc squared. So you got to be persistent. I mean, it's very important. So all of this sounds, I must say, very strange indeed. And unless you go through this analysis I was trying to show you before, you realize that what he's coming down to is the fact that the light has a finite speed. It changes the way people measure things. You think you know what you're doing when you synchronize your clocks, but in somebody else's frame of reference, you haven't really in his frame of reference, your clocks are not synchronized, and that changes things a lot. So the fact is that the theory has been tested to very great precision in many cases, and has held up despite the criticism, despite people scratching their heads and say it can't be true. Well, I don't know if I've given really gone through the examples, but they are in my notes and in the book, where people have explained the fact that moving things seem to live longer than if they're at rest. So the fact that you have a clock, a moving thing, which is going to decay in a certain time in its frame of reference, when seen in another frame of reference against which it is moving, the time in its own frame is the proper frame, the proper time, and the proper time is the tiniest, right? So that time is the shortest. As seen in any other frame of reference, that process will look longer. That's the rule that you want to remember. The proper time is tiniest. So a moving particle coming from outer space and it's going to decay in its own frame will be a tiny time. In our frame, it'll be a longer time. And that has been experimentally observed and very precisely, well, reasonably precise. It's a statistical thing because things don't decay all exactly at the same time. There's probability. But within that accuracy, that's been confirmed. Space contraction is observed. Velocity addition, there's a very nice experiment that was done well before Einstein's theory. This Fizeau experiment was very interesting. 1851, this Fizeau was able to send light two ways through moving water, and the water was carrying the light. So you sort of get an addition of the velocity in the water compared to velocity going sort of the other way. And he got a result which people didn't quite understand, but it comes directly out of Einstein's relativity with an easy explanation. And there's a variety of other things. So this theory is now deeply embedded in physics, such that the criterion for a good theory is that it has to be in agreement with special relativity, or else we reject the theory. Until further notice, as science is. If somebody comes up with a reason that it's wrong, well, okay, it'll be wrong, and that's the way it is. And again, I did sort of at the end of the class point out to you that this idea is so strange in a way, and it's also misunderstood so much that please don't get it confused. It only talks about things in relative motion. As I said, there were some religious people who thought that there was something bad about it because it said everything was relative. No, everything is not relative. The morals are not necessarily relative. It doesn't talk about morals. It talks about two things, like a train moving on its tracks. That's all. Or a rocket ship moving, or a fast-moving particle. That's what relativity is about. And it's not about other things. But people have a way of stretching into other realms. So don't be misled by that. In fact, some things in the relativity theory are not relative. We said, of course, the speed of light. Electric charge is very interesting. Electric charge does not change regardless of the speed at which you move. That will be a constant. And also, Einstein's theory is very causal in the sense that it give me the speed of the relative motion of two things, and I will tell you the length that you'll measure in each of those frames of reference to the precision that is possible. But it's causal and it's precise. In fact, Einstein stuck to this idea. In fact, that's why he criticized quantum theory. Although he helped start quantum theory, he didn't like the idea that quantum theory was statistical and that you couldn't give a precise answer to, for example, when an atom might send out a bit of light. Let's say you shine light in, when will the light come out? That's kind of a statistical thing in quantum theory. There's a probability. It will come out roughly at this time, but it may come out a little sooner or a little later. He didn't like that. He said, well, you should know when it'll come out. You just don't know enough about that atom. If you really know everything about the atom and you send light in, you should be able to say exactly when it'll come out. He liked that idea, strict causality. And he fought with Niels Bohr all the time about this kind of issue. They were friends, but friendly argued with each other about things, and Einstein didn't like some of the ways quantum theory was going. So far, quantum theory stood up against Einstein's arguments, though. As we'll see as we get into it. I think that's enough I want to say. Maybe you didn't hear my story about the fact that Einstein's only contribution to the weapon was warning President Roosevelt. And you see the date of this letter, August 2nd, 1939, which was the war, Second World War started September 1st, 1939. That's when Germany attacked Poland. So just before the war, Einstein, at the behest of his friend Szilard, very close associate of his, and Enrico Fermi, who knew about this new development of fission, trying to get the United States to get prepared that possibly Germany might build this super weapon. And so that was his contribution. Okay, so let me move on, if I may, to I want to talk about, okay, I'm going to go back from here. Next week we're going to be doing a lab on diffraction interference, and we should do this. This is a very interesting subject. I think it's much more concrete than dealing with relativity. It's much more direct. And so this is chapter 32, and it's something we referred to before, namely that waves can interfere with each other, meaning that if you have a crest and a trough of a wave, they can cancel out, and you can add like 1 and 1 and get 0, which is characteristic of the wave. So we're going to just use that particular property in, first we'll understand where it comes from in some detail, and then we'll just apply it to a bunch of cases, like if you have 2 slits, or many slits, or a periodic array of things, which acts on kind of like slits. And even 1 slit can give you this, or a circular aperture, or even a thin film can give you these kind of interference effects. And the other thing I did want to mention, which isn't mentioned in the book, and I don't know why, is another phenomenon of light, namely it's scattered, which is the explanation of why the sky is blue. I mean, it might be nice. That's something we're familiar with, so why don't we understand it in this course? So, and red sunsets. Sounds very poetic, but we should understand the physics. It doesn't detract from the beauty of a red sunset to know physics. Okay, so again, these are general properties of the waves, of wave phenomena. It's down here in my list, diffraction, interference. We've seen how a lot of these things we've been over, reflection, internal reflection. The frustrated part, I haven't quite got to deeply yet, but we won't worry about that. Refraction, we talked about, the bending of light through lenses and so on. So now we're going to talk about diffraction, interference. And again, if you have a wave, it should diffract and it should interfere. So let's see. So we'll talk about light in particular, but actually I have some setups here using microwaves, which are, again, electromagnetic waves. They're just not visible to us. They have a wavelength about 3 centimeters, something like that, an inch. But they're electromagnetic, and they're a wave. That's all. It doesn't matter that they be electromagnetic. If it was a sound wave, you could get interference and diffraction. Or a water wave. Doesn't matter. That's the beauty. It's everything. So the idea is, though, that you are dealing with a wave which sort of has to add to itself in a nice, simple way. And the way you do that, you have to have what's called a coherent wave, but you couldn't have like one wave like this and another wave like that, and they will superpose, but you won't get simple interference. Something like this is actually will give you a superposition in a funny way, but it can't cancel everywhere. In other words, a wave like this could not cancel a wave like this every place, right? I mean, it doesn't seem possible. Whereas if the wave were sort of a replica of itself, you can imagine it canceling. For example, if I had these two, I could imagine adding these two, and I get a bigger one. On the other hand, suppose that this wave came in counter, exactly the same shape and the same size. This would add to that and cancel out. So let me get rid of this obnoxious one here. Yeah, so if I could get something like this, you could see where if this were the amplitude of the wave, and I put in a wave of similar amplitude, but what we call out of phase. This would be 180 degrees out of phase. See, this is one wavelength, so we think of that as 360 degrees. Namely, it would be that shape of a rotating arrow going around 360 degrees would generate a high point, a low point here, a negative point here, another 0 over here, and that would be, and then come back to, well, depends where you start. If you start from here, we should come back to here. This would be one wavelength. Right? And we speak of it in degrees, starting from anywhere. You know, you could start from here. This would be a cosine wave, and it starts out at 0 degrees. And here, if I started from here, it would be a sine wave. It starts out at 0 degrees, but it repeats after 360 degrees. Okay? And we could add these two if they had the same amplitude, and they would cancel point for point. The question is, how do you get two waves that are so perfectly alike? It's not obvious, but in a way it is. A simple way of doing it is you start out with a wave. Let's say you had an ocean wave coming in, and here's the crests and troughs of this wave. The way I could get two such waves is if I put a barrier, something like this. And so my wave comes through, and I have a wave coming through here, and I have a wave, this wave has come through the barrier. So now this is really the same wave, just part of it. And so from here on out, I have two separate waves, and they are peak for peak the same. Okay, so that's one way of doing it. And okay, so now I know how to make what's called a coherent wave. I can get two things which